So we're at day 2 for chapter 2, the circular motion chapter, and today we're going to go beyond looking at the acceleration for something that goes in a circle. We're going to start to look at the forces that are involved. It's kind of a 3-lesson long process, and here we go. So the first thing, just a little vocabulary. Sometimes you'll hear people talk about the centripetal force. Of course, centripetal means center seeking. But what's important to know is that this isn't some fancy new force that you need to add to your free body diagram. In fact, it should never get added to your free body diagram because it's actually just another name for net force. That's all it is. It's optional. You don't have to use it. You could always just continue to say net force. But sometimes when people are doing questions that are working with circular motion, they like to say centripetal force instead of net force. I guarantee you that since the acceleration of the object will be towards the center, that when you add up all of the forces on your free body diagram, you will find that there is more force towards the center than there is away. So the centripetal force, the net force, overall will end up towards the center, and that's the direction we're going to call positive. Just like net force, because it is net force, you should never be adding force to your free body diagram and labeling it as centripetal force, because it's not a real thing. It's just a bookkeeping idea of adding all of the forces that are out there together. Okay, so what do we got here? We've always been working with F net is equal to ma, and the whole idea is you draw a free body diagram to establish what F net is. It's going to be the same deal, except if you wish, it's optional, if you wish, we're going to name change F net to Fc, the centripetal force. And some people like to put a little c subscript on the a, just to really emphasize that this is circular acceleration, centripetal acceleration. You don't have to do that. You can just continue to work with F net equals ma if you want, but you can do this if you desire. Now, the neat thing in this chapter is there are only 2 ways that you can find the acceleration that we've been working with, either v squared over r or 4 pi squared r over t squared. So when you go to do F net equals ma, you're going to find that it always turns into one of these 2 forms. It'll be the net force is equal to mass times v squared over r, or the net force is equal to mass times the 4 pi squared r over t squared. Basically, if the question's talking about speed or asking about speed, use this one. Or if the question's talking about period or asking for period, use the second one. And that's going to be our plan. And now what we need to do is just, like I said, spend about 3 days looking at some free body diagrams of various forms. We'll start off with the most simple, and then we'll progressively look at more and more interesting ones. So we're going to find that towards the center is always the winning direction. So let's call that direction positive when we go to do F net equals ma. Here's the simplest possible free body diagram, the simplest possible story. Imagine somebody is just spinning a ball around with a string in a horizontal circle. Now, I know gravity would tend to pull it down a little bit, but let's just ignore that. Let's say compared to the tension force, that gravity is actually negligible. Or you can imagine that you're actually in outer space, and there's just no gravity around, and you're just spinning this thing around in a nice flat circle with the string. Tension would definitely be acting on that object, pulling it in towards the center. And the neat thing about this story, that's it. There is no other force, just the tension that's acting on this ball. So we stare at it, we eyeball this thing and say, okay, what does that all add up to? And the answer is, it adds up to tension. So when you go to do F net equals ma, or if you wish, Fc equals mac, what you're going to do is just substitute tension in for that net force, because that's the only thing that we see on that left-hand side in that picture. Now, you might choose to go with the speed version, or maybe the period version for A, whatever works best for you. A little caution, we now do have 2 capital T's showing up in this story. And of course, you'll have to be careful because this one here is actually about tension, and this one here is actually about period. Okay, but I think in context, just based on their position, it should be pretty easy to figure out who's who. Okay, let's try one of these out. Let's say you've got a 3 kilogram mass, and it's rotated in a nice little flat circle, and the radius is 2.1 meters. Now, down the road, maybe they might say, oh, the diameter is 4.2, right? But right now, they're just offering you the radius. That's great. And they're saying, oh yeah, the tension in the rope is 920 newtons. And they're wondering, how many rotations does it make per minute? This is kind of sounding like that whole RPM thing, right? How many can it do in a minute? Let's go and find the period first, and then we can find out how many it'll do in a minute. So looking at F net equals ma, again, very simple free body diagram. We only have the tension, so that's going to go in on the left. Got our 920 newtons, and then it's just plug and play, and then we're looking for the period. Yeah, it's quadratic, but we can just take a square root of the t squared and at least have figured out what the period is in this story. We're not quite done because it did ask for rotations per minute, the RPMs. No problem. We can just go back to our Physics 11 understanding of frequency and period and say, well, period is some random time divided by the number of cycles that happen. And so my random time, my lowercase t, can be 60 seconds for a minute. And then a quick solution there, and you find that, yeah, this thing will do 115 RPM, 115 rotations in a minute. So that's going to be our plan for dealing with RPMs. Just wait, go with period first, and then you can switch it over and do RPMs later. Or if they offer you RPMs, just switch it right away to period and then proceed from there. Okay, the next free body diagram. Getting a little more interesting. What if you're standing on the Earth and you take a string and a little object on the end and you start twirling it around in a vertical circle? Now in university you'll start to take a look at this story all the way along the circular path, but for us we're just going to take a look at the object at the top and the bottom of that little vertical spin. Up at the top you're going to have gravity pulling down on the object, and you'll have the rope pulling down on the object. And down is good. Anything towards the center is positive, right? I like to put a little X by the center just to remind myself that, yeah, X marks the spot. That's going to be the positive direction. So when I go to change this F net into what I'm actually seeing, my idea here, I look at the story and go, hey, we've actually got tension and the weight working together. And so that'll be my story for the top of the circle. At the bottom of the circle, the tension and the weight are going to be in a battle, and towards the center is going to win. So when I go and establish my positives and negatives, I'm going to call the tension in that part of the story positive, and I'm going to call the mg negative here because it's away from the center. So anything going towards the center is positive, things away are negative, and then I can go t minus mg is equal to mass times acceleration. And of course, when you're doing these problems for that A, you can use whatever version works best, whether it's the period one or whether it's the velocity one. Totally up to you. Okay, let's try one out. It's getting a little more interesting here. We've got 200 grams, all right, so that's going to be a 3 decimal place shift. Still a radius, 1.5 meters. Okay, so nobody's trying to trick us with diameter. And they're saying the speed at the top is going to be 4.5 meters per second, and they're wondering, well, how tight will this string be? No problem. Looking back at our notes here, we're going to have tension and mg working together. We will change that to 0.2 kilograms, and we're ready to go. So F net in that picture was tension plus the mg working together. That's going to make that mass accelerate. Don't cancel the m's here. There is no m on that tension term, so we don't have that option of just throwing the m's away. But we could plug the numbers in. Things work out pretty well. Looks like that tension is going to have to be 0.74 newtons as it goes over the top of that circle. An interesting question might be, what would happen in this story if we were to start slowing this thing down? What if we went at 4.4 or 4.3 meters per second or 4.2? What would happen to the tension? We can kind of play our checks and arrows game. If that number starts to drop, and if you've got exactly the same radius, same mass, and you're on the same planet, what we can see is this right-hand side is going to get smaller. And if that right-hand side gets smaller, the left-hand side has to get smaller as well. The mg is pretty stable at 1.96, so it would have to be the tension that would actually be getting smaller in order to make that happen. And it would continue to do that as you went slower and slower until finally the tension would actually hit 0, and the string would actually go slack as it goes over the top, right? And then the story doesn't really behave like a circle anymore, so you'd kind of have to stop. Okay, next free body diagram. We're going to take a look at riders on Ferris wheels and skiing through little dips and over bumps. Turns out it's actually the same story, so we'll lump them together into part 3. I want you to imagine that these skiers and snowboarders are going through little semicircular parts here, right? Little parts of circles as they go through the dip and over the top. The skier going through the dip, taking a look at the forces acting on them. On any other day, if you were just standing around in the parking lot at the ski hill, you would expect the normal force to choose to be the same size as the mg. Normal forces don't have to do that. In an elevator, the normal force is larger sometimes than the mg when it goes to launch you up into the air, when it goes to accelerate the elevator. But as this rider goes through the dip, they are going to be accelerating. If they were not, they would actually go straight and they would plow into this snowbank. That wouldn't be any good. So what happens here is the snow pushes up extra hard and you can feel it in your knees. And so you have Fn winning compared to the mg. Now I've put my little magic X there, right? X marks the spot for the direction that's positive. So if I was doing this skier or a car going through a dip like that, I would be going Fn minus mg in order to set up my Fnet. For a skier going over a rise like this, assuming they're still in contact with the snow, you'd have the Fn kind of throwing the game, agreeing to let the mg win. The mg can't change its size, not very easily. So the mg being stable means the Fn has to go small in order to let the mg win. I'm going to call towards the x positive. So for this story here, this is where you would have mg positive minus an Fn that's negative, and then whatever version of acceleration you choose. Let's try one of these out. Trying to find the normal force on a skier. They're going pretty fast, 14 meters per second through a little circular dip. The radius is 18. Okay, so if I am at the bottom, as you've seen in the free body diagram, I'm going to have Fn minus the mg equals mv squared over r. And now it's really just plug and play. Okay, the only thing we were missing is the normal force up. If you were just standing around, this skier would experience a normal force of 735 newtons, just equal to their weight. But here the normal force is much bigger than their weight because it not only has to balance out their weight, but it has to provide extra force in order to get that skier to accelerate towards the center. Okay, Ferris wheels. They're the same story. In a minute we're going to do roller coasters that can go upside down. But right now this is a Ferris wheel, and the neat thing about a Ferris wheel is that the seat never gets above you. It always stays underneath you. But towards the center has to win. If you're going at a constant motion in a circle, there has to be acceleration towards the center. So at the top, the mg is what it always is, and the Fn, the force from the seat up on your bum, is actually going to diminish to allow the mg to win. And the mg is the winner here, right? Towards the center wins. So we would go mg minus Fn at the top of the Ferris wheel, just like we did on the top of the rise for the skier. And then whatever choice of A you prefer. At the bottom of the Ferris wheel, just like the skier in the bottom of the dip, we're going to have the Fn working extra hard in order to accelerate you towards the center. So at the bottom, Fn is now positive because it's towards the center and it's bigger than the mg, and that's how I would set it up. So notice that there's a difference here, right? At the bottom it's Fn minus mg, and at the top it's mg minus Fn. And that's critical. You can't put that in the wrong way and expect to get the right answer. You might think, well, I'll just get the right answer, but it'll be negative. No, you won't. You're just going to get some random, bizarre number that's meaningless. So you do have to set that Fnet up correctly. Let's try this out. We could do one where we try to find the normal force like we did for the skier, but I want to deal with this issue, right? What if the person gets off the ride and says, hey, it felt like I was weightless? Well, you weren't actually weightless because weight is the force of gravity, so you still had a force of gravity. But maybe you didn't have an Fn acting up on your body, and it creates this feeling of weightlessness. And so the question here is, how fast would you have to go so that up at the top you actually feel like you're weightless? Okay, so really that idea of apparent weightlessness means that you're sitting there with no Fn, that the Fn is 0. Okay, up at the top, traditionally, I would draw this, and maybe I'd normally be finding a value for Fn, but this time the Fn is going to go to, based on this example, is going to go to 0. So with the Fn gone, it actually gets kind of interesting because now every term that's left does have a mass. So now that the Fn is gone in this story, because it's got this very special description here, we could actually go and cancel the m's in the remaining algebra. What happens is this 4 pi squared r over t squared, that circular acceleration, is actually just matching gravity. So gravity is forming the top part of that circle. And gravity normally does parabolas for you, but here the top part of that parabola looks very circular-like. And it looks like the period would have to be 5.68 seconds in order for this to work. If you were to go with that period, you'd find that you're just floating above your seat at the very top of the Ferris wheel, okay, as it goes over the top of the circle. Okay, let's also take a look at a roller coaster. Same story down on the bottom. Once it starts to curve, or when it's finishing its curve, you're going to feel extra Fn. But up at the top is different than a Ferris wheel because a roller coaster that's looping can get the seat up above you. So when the seat pushes on your body, it will actually be pushing down on your body up at the top. And they do that with roller coasters. They make them go so fast that you wouldn't need a seatbelt unless the thing got stuck. In fact, you still need the seat to push down because gravity doesn't push down hard enough. So up at the top, the Fn, if you can see that there, the Fn is down, and so is the mg. And so you have Fn plus mg equaling mass times acceleration at the top of your roller coaster. At the bottom of your roller coaster, you're going to have Fn winning the game. And it'll do that right up until you get to the flat section. Then the Fn and the mg will match. But during the curve, just as you're finishing the loop off, you're going to find that the Fn is bigger. And if you go Fn minus mg, that would be winners minus losers. And that's going to equal mass times acceleration. Okay, let's try one out here. At the top of a 7.5 meter radius loop, 60 kilogram rider feels a seat cushion force of a lot, 1460. They must be really flying through this loop. And I'm wondering what the roller coaster speed would be. Okay, well, if I'm sitting there at the top, that's when the seat can actually get up above me, and the seat can push down on my body. So I'd have Fn acting down, so does the mg. They're working together to make me go in that tight little circle, and it's going to make that mass accelerate. Since they're talking about trying to find the speed, I'm going to choose to use this v squared over r version. Plug and play. I couldn't quite fit it all on the page there. I had to just wrap it around a bit. Throwing the numbers in, it all falls apart pretty fast. It looks like that roller coaster is actually going at 16 meters per second. And at that speed, that's when that seat cushion is necessary because gravity alone won't make you go in a tight enough circular top, so you'll actually need the seat cushion pushing down as well. Okay, last part here. At what speed will the rider be just barely held in their seat? Right? There's that same story again, right, where the Fn is 0. So normally, you'd be going Fn plus mg up at the top, but this time we're going to wipe out the Fn. And again, we can see that once the mass is gone, it's mass independent, you have gravity performing that acceleration for you. And in this story, it's 8.57. So what was the last example there? 16? Yeah, 16 meters per second on the previous example. And the seat cushion really has to push down on you. And in this one, you wouldn't need the seat cushion to push down at 8.57. But don't go any slower, or you'll start to flop out of the seat. Okay, and that would be uncomfortable. And that marks the end of the first of 3 days of some free body diagrams, and we'll look at a few more, a couple more amusement park rides maybe, for the next couple of days.